So okay, the date now is the, the date now is the 2nd of February 2026. The time now is 11:46 a.m. Okay, so Namdi, you're talking to yourself right now. So what's the video about? What's the show? So this video is about Bluetooth is hard to roll. The Bluetooth is so hard to rub out, guys. It's so hard to roll the Bluetooth. So there, in Siggy, uh, in Siggy, Trident, Trident, Interpreter, Cisco, Cisco, Cisco model, Cisco. So again, um, Siggy is a human rights in Siggy, anything about necessary as a go. I think it's a human rights protocol. So basically, it's basically pointer allocation for need problem. So you get OBI and you get OBI is vector to SA is vector OBI SA and Uche. But it's basically allocation saves stuff from it's basically we're talking about the execution order now. Execution it goes with the about the execution. Um, Basically it's called the 1/2 minus 1 minus 1 over two dimensions or two pointers of value. So I'm going to give my little formula. So 1 over so you have the system of one. So you have it's basically a trust system of who holds the lock. Who holds the lock? OBI can hold a lock. SC can hold a lock. Which can hold a lock. But you don't want a lock. You want a time capsule. You don't even lock anything. You're supposed to waste time to you know, so you get the standard s squared plus y squared equals t squared, where t is the time, and x y. You get y equals negative void plus or minus square root of b squared minus 4ac over 2a. So, this is a formula here for pro formula, But the goal of this video is to have a system that preserves the dimension, without locking it. So you get 1/1 dimension. So, for example, you have the formula, you get -1. So you have consensus, trident consists of 0, 0, 0, 0, 0, 0. And if you have 0, the only thing you have to do is 0 minus 1. So you have 0 or epsilon. So you get three binary, three parity numbers, three numbers, 0, 0, 0. OBI has 0, 0, 0, or epsilon, epsilon, epsilon. SA has epsilon, epsilon, 0, or 0, 0, 0, and Uche has 0, 0, 0, 0, 0, 0. There's three numbers in total. So I'm trying to give a formula. So if I have a -1, I'm talking about consensus. So -1. So if I have a 1, I'm actively operating. If I have a -1, I have a pointer to 1 to an operation that's holding. So the -1 symbolizes a holding operation. So if I have a 1, if I have a 1, I give you a -1, and you hold that space for me. This is a holding operation. If you have a hold, you have a hold, you have a pause. So I'm saying to you, you have a hold, so you can hold something that hold space in memory, and indefinitely. Look at a -1. If you have a 0, you have a 0. That means to be to graphic state of -1. 0, 1 can have a -1. So 0, 1 can have a -1 or epsilon. So I give you a state of things. So -1. So you get 2 -1, which is here for 0 or 1. So the -1 matrix is basically actually again you can't have. So you have two others. So I'm giving you instruction. So I give you. So I have a 0 or a 1. I give you, then you have to hold space for me to speak. Basically, it's the inverse computation of the standard oppressive lock, giving someone a softball and asking them to speak. What about if everyone gets a softball, and I'm the only one not to speak? If I have a softball, and I'm not, if I have a hard ball, so a hard ball, I shouldn't be speaking. So get a softball, duality, a softball, which is I have to speak, and I get a hard ball. But I cannot give you a hard ball. So a hard ball would be like a baseball, like a tennis ball. Tennis ball. So if I have a tennis ball and I give you a tennis ball, you're allowed to hold that space for me to speak. But it's an interesting program. But what's an opposite lock? So it was a space lock. So it's a space lock, which locks out space and time. Lock. And here s squared plus y squared equals t squared, where t is the space and s squared is the time. S squared is the time. So this is space and time duality. This space versus time first. First. What's the goal? What am I looking out of? So this is called a time capsule. So even with some equation, they evaluate to the parabola equation, but they take time to calculate the integral of the time it takes to. So it's maybe via the OBS derivative system repository. So I have a one. I have a one. I have a one. I give you. You hold. I have a one. So I'm about to speak. I'm speaking. So who's speaking? Who be speaking? That means I give. Okay. Let's say S is speaking. S is speaking. S is want to say something. He has to give two orders. He has to give. Say the instruction is S wants to output. S wants to send a message, a control, a command. Say here I am here and now. Here now. Now. So let's just say now. So let's say here, HERE. So here underscore now underscore underscore here. Now, here space now. So as I said, here space now, here space now. So as he's saying here and now, but he's saying in the term. So the term can be Cisco bottom up or parallel. So because Cisco is an execution order. So what is here? Let's just do this here now. Let's just use arithmetic operator. So let's take away here now and say let's use our polar system. The polar system I'm going to give is x, y, z. So I'm going to say latitude, let's say the 2y plus 2y squared. So I'm saying a squared plus ax squared plus 2y plus 3. So the triangle resolver is basically so x is trying to find its position on the map, where it is. So I'm gonna try to solve it, but what way so a is 6, 7x squared. So 7x squared plus 2y plus 3. 7x squared plus 2y plus 3. But s is one commanding and controlling it. So s is which is 7x squared, 7x squared plus 2y plus 3. But this one. So I'm trying to form. I'm trying to find 2y. As you can see, this is solvable. So let me try to sit down on paper and solve on paper. SJ says SJ is basically a coordinate system. So we can plug the y and x squared to find the space and time SJ is existing. The space formula is the area, so you can work with the area. So the area basically the area is where, but this is all referential via dimension of half. So half a dimension should be dimension, half your dimension, half to two, and scale. So your dimension yourself, so you get a half the space, half of x, and scale two of half of x to the ratio half to two, and the two would be halving your dimension of space, halving your dimension of space, and you have to grow your grow yourself. No. So example, if I'm a, again, if I'm in a 3D world, 3D divided by 2, 3 divided by 2 is 1.5 dimension. So now I now existing now I have I now have half the dimension space to operate. I'm not computing on 1.5 dimension. But if I now 1.5 to 2, if I scale 2, if I times by 2, I get 3 again. Now I'm now operating in the 3D space again of x y z. So that's how that works. So you're transcending the dimension. If you start so you can compute any dimension that's a u. So you can take another dimension and x y z and copy it over the system of the part. So that's a, so for every pathway, shape, or form. For every path, shape, or form, it's really you're gonna have half the dimension, half the properties, half of everything, and compute in halves. Before you scale to the system of non-unity. So everything in the board sorted out. But the main problem I was saying to you guys, let me show you the board here. Is you have let me tell you what you guys. You have to understand the problem really before I can step into the paperwork. So you have OBI 000, SA 000, but these zeros represent having 0 bytes, 000, nothing, and which has 0002, which has 0002, yes, which has 000. So they also have zero, but no, this zero they hold it in mind, they don't speak them. So the extension order has to be, which is this thing I'm trying to say is here, referring to you. So, you know, So basically, if they don't have a, they have a, don't have a, they don't have two type of coding system. They have a problem of these are just channels. Channels. These are just channel zero, channel one, but it's not actually the full person. It's like a chat relay system. So they have x squared plus y squared equals t squared, which is tan, and or space squared, or space squared, which is the space, and then y squared equals minus negative b plus or minus square root of b squared minus 4ac divided by 2a, which is the parabola equation for the time curve. And now you have the half a space or half of a time in dimension to compute over to or depending on the project you're working on to the two space. So you can use them both ways. You have to prioritize the dimensions and the time. Half of the space represents half of the time represent the half of the time for that operation you're performing over the space you're in. And this is how the time works. So you're trying to do things in half to block people out of the system, and then you have this equation: 7x squared plus 2y plus 3 equals a location for Eze. So this will be Eze's location. Eze's location. So Eze's location is the physical, but you can always get a signal. You can always get come here. So he cannot be locked out because so the next step, so the kind of hold is so if so LJ is equals Eze's location and Eze has 0 0, and the other problem is that the Eze wants to when other problem is this, so Eze has 0 0 0, so Eze has to give up space or time to OBI. So he has to hold. He has to hold. So when Eze speaks, he has to hold the space, and by holding the space, that means he has to give his zero. He has to give a one in time. He has to give the equivalent of the time he's going to speak. By holding them by the amount of holding he's gonna do of the radio signal to give a message on. You have to hold the channel. You have to hold the channel to speak. So by holding a radio signal, you have to give some time to speak. But that time cannot be run out. It must not run out. The more you hold it, the more time you get. So that's the goal of this. So the integration of that to be so minus one. So that'll be minus one. So as you can see, a minus one here. So he's gonna give OB a one. He speaks to OB and Eze a one. Is it one? Because you even said if speaking to Ezra, but they hold a matrix of a matrix of a negative matrix. So you have a conjugate matrix, but it's not own conjugate matrix muscle. So my matrix works like this. So you have a vector minus one. Yeah, you get number one and one. But this number has so this one on one has a conjugate. So you have to have to the power of negative one. And that's operating over. So the power of negative one will give you the inverse matrix over negative one. That will give you one. So if you have one to the power of negative one, you get one to the power of negative one. Will give you 1 to the power of negative 1 will give you 1 to the power of negative 1. 1 to the power of negative 1 is 0, 0. So S will get another 0. So since S gets 0, I mean, since OBI gets 0, he has an extra 0 to hold that space until he can send that byte back. So the 0 represents OBI, O for Oscar, B for Bravo, I for India. So SA, E for Echo, Z for Zebra gave OBI a 0, a 0, 0, but he gave him two zeros in the form of a vector. So this is a conjugate pair model because you can have conjugate pairs in this model too. So it's inclusive. It's not it doesn't exclude a system of conjugate pairs. So you have two zeros. So as it gives as it starts to speak, when you start holding on the radio signal, by holding I mean literally you're holding down the kind of response relay system for the radio. So as it gives a 0. As he starts speaking, he has some space ahead of time. So he already gives two zeros. He gives two zeros, which are two consent zeros. So he gives a consent, two zeros, not consensus, two zeros, which represent permission, consent, and consensus, which is a need. So as it gives two zeros, which becomes minus one, 0 squared, 0. So he has minus one to the power. So he gives you so OBI holds 1 0, and Uche, U for umbrella, C for Charlie, TH for hamburger, E for echo on channel 3 has another 0. So the goal I'm to define this formally, guys. So the whole thing, the whole system of saying works because it's unilateral. I hope I'm using the term lateral. It works in kind of structure. So let me get my bag, guys, because someone's here. I don't know where it came from. No, I don't know where it came from. So it's basically a system of resolving consensus because consensus is needed, not wanted, and you can never hold a consensus you're not given. You can never hold consensus indefinitely if you're not given. And so like I was saying to you guys, you just find the thing I'm looking for, guys. Mom. Oh, okay, good. So so you have consensus. So you have my one. So my one is not your 0. We share a relationship. We really have consensus already. So we have consensus. But I give you for to do operation. So so I get minus 1 to the power of to the power of 1. The power of 1 is 0. Well, negative 1 is 0, 0. But the signature negative represents you holding something for me. So if I have a negative 0, I can have nothing. If I have a negative, if I give me a negative, that means it's only a negative one. So I have to hold the space, and that space is two zeros two negative one you gave to me. So you cannot give me your one because your one is my negative one. You have to give me your one. So that'll give so we have zero 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 zero. Zero. So the goal is to resolve the trial system. So for example, you have an XOR operator, and this is most XOR basically this. Oh, so you have so I give you so you give me so Eze gives Obi I X equals OBI. So exclusive operator. So Eze has a one. Eze has a negative one. Eze has a zero. Eze has a zero. Eze has a zero. But he gives has zero zero zero, which has a zero zero, and then Eze wants to give OBI two ones, one one. So and then now OBI is going to minus one. So he ends up giving OBI negative one, two negative one. So that means negative one squared. Negative one, negative one, negative one. Which OBI interprets as negative one, which OBI should interpret as negative one, as one one, but to the power of one, one one, or to the power of one, positive and negative one, which is the conjugate rule. So the positive and negative one is the arbitrary rule and the guilty rule that he uses to determine the interpretation. Which is just operation of negative. So this can be the endingness of the system, but it's a bipolar resolution system. For example, OBI will have to use matrix of negative one and positive one and the whole of negative one squared of zero. So OBI will see negative one, and negative one will be his zero, his zero, because negative one to the power of one to the power of negative one is zero. He gets two more zeros. He gets two more zeros, and these zeros is basically which is one. So he has to hold this space in time, this time in space, and space in time. So before they start communicating, before they start communicating, or if you have if you have so which you can give this negative one one, we can give a negative one too. So you can give one, you can give consent, you can give consent to OBI and Uche. So Uche is in channel three, OBI is in channel one. So you can give one to OBI, one to Uche, but the goal is to have the system resolve itself tomographically. So one. So Uche and OBI gets a one now. One. So what do they do that? How do computers do this? They have time and space and time. So they have to compute the time and space then he needs before he starts computing. Because the time, the amount of time you're holding the system for before it's set. So basically it's a sense system. So how much time have I recorded we're talking about? And how much space do I need for that? So if OBI holds radio signal for holds the channel here for the time of 30 seconds, 15 seconds, and 15 seconds for every 4 bytes allocated. 4 bytes, which would be 4 times 8, 8 times 4, 8, 8 times 4 is 32. That'll be 15 seconds per 15 divided by 32. 15 divided by 32. The bit rate will be 0.46875. But this is not the good way, so you have to have half the time. So there's a ratio between the space and the time. The share as dimension, so the time is in the space. So if you have 15 seconds, you have the time, maximum time, but you have the space, time in space. So, and space, you have the space in the time. And the space is basically half the time. So that's basically half the time. So half the time would be half the dimension of time in space, how space and time would be 15 seconds, which is basically 0.4867 bit rate. I take the third derivative of this constant. So basically, I start, because I'm doing it wrong because it's lunchtime. But the goal is to use the coordinate equation to coordinate. First of all, first step, basically, I have to continue to after the lunch. But so I have to use. First step is to use x squared plus y squared equals t squared. You get a parabola, and you have y equals minus b squared. This is the first step. Y equals minus b squared, the square root plus or minus square root of b squared minus 4ac over 2ac. This is the first step to determine y and x in space and time. And then you have the where they are in the physical, where they are, because basically it's meant to send. Before you can't send it. You can't send a message before you know where you are. So that's the goal. You can't send it. The message can be hijacked or jammed. So you have to send the message before you know. So you get seven. You get seven x squared. No, 7y squared plus 2x plus 3 equals t. T is the space and time that they use in space and time. So that's the formula. And you get half of that space in time. And so if you have half of something and then you then double it, you then scale it. But if you enlarge something by half, enlargement by half, enlarge something by half, and then you scale something by double the half, you scale it up. Technically, you get the same structure you have, and that's how that works. So first step again, take the parabola equation of x squared plus y squared equals t squared in space and time. Then find where you are in space. For example, which SA is 7y squared plus 2x plus 3 equals t in space and time, and you have half of the dimension. Then you can have the computation of the system of holding. So the goal is to have the system holding space in time and time in space for the communication matter before its execution. So the execution is the goal of it, but the execution is with the executing running in the system, because I can say something and then do that thing. So once the finish doing it, the system does it. It's a radio system that does it. And this is the parity model of 000, and the trying way of holding. So so you can have another matrix like minus 5. You can get 5, 2, 5 minus 2, 5 minus 2. But that minus 2, let's try this one. You have 5 to the power of negative 1. 5 to the power of 0 is 1. 5 to, so if you have if it consists of power, so you get 5 to the power of or negative 1. 5 to the power of negative 1 is 5 to the power of 5 to the power of 5 to the power of square brackets negative 1 is 0.2. Is 0.2. And you get 5 to the power of 1. Oh, which is a half. So you get a half. So you get 5 to the power of a half. So you have the lower of a half. So you can get 5 divided by 2. And you get 2.5. You get 0.2 because it's a half. This is negative 1. You just inverse the dimension. So you have a quantity that's quantifiable by ratio. So you can have 5 to the power of a half. Let's try that. 5 to the power of 1 divided by 2. Close bracket, and that's 0.5. But 0.5 doesn't tell the full story. You can have 5 to the power of 2 divided by 1. I have 2 to the 5. But the goal is to have system resolve itself dynamically. So the consistent matrix is to the power of 0, minus 1, and 1. And they have access. So if you get 5 to the power of minus 1, you have 5 to the power of 5 to the power of 5 to the power of minus 1 of minus 1, you get 0.2. If you have 5 to the power of 0, you get 1, and 5 to the power of 1 is 5. So you have three axes that hold the half dimension, 1 divided by 2, and you can have stop processing, and you get 5 to the power of 2. So 2 is scale, 2 is inverse of scale, so 5 to the power of 1 based on the execution order. Also, if you get the matrix 5, you have the conjugate negative 5. So you can do negative 5 to the power of negative 1, which is negative 0.2. So it works the same way. So you get a range from 0.2 to the 1. You have negative 2 to the power of negative 1, you get negative 0.5. And that will be 0.5 is because you watch the half, so watch the half. And that's basically perfect. Thank you, Monday. I love it too. So 2 to the power of 1 will be of negative 1 will be 0.5. But that's really zero point 0.5, just halfway because it goes to the half. So it tells you the growth factor over E. So let's try E, epsilon. Let's try the number E. E, E to the power of square root of negative 1 will give me 0. Basically, this is the ratio of the 0.3678, which tells me the growth factor of a unit. So it tells me the growth factor of a unit. So the growth of something before it happens. So this is what it tells you because this is why it's scale. So basically, this is a matrix system. This is like a conjugate system for matrices. So I did E, which is identity, the which Euler's number 2.718281, and I get to the power of negative 1 0.367879 or 795, 793. So this will give me the growth factor of a unit. And the unit is dynamic controllable too. So you can have it grow linearly or non-linearly via polar Laplace rules. Thank you guys for watching this video. I go have my lunch now. Thank you for this video. Like, share, and subscribe. If you don't like it, don't like, share, and subscribe. Leave a comment, dislike, and like, share. Just keep communion. I'm not scared of any likes, but it's a consistent system. Consistent system. So the goal is to have memory held when you're not needed, when you're not needed, when you don't need it, to have memory held for you. So have memory to just help in place before you compute something via trident interpretation. Thank you guys for watching the video. Like, share, and subscribe if you like.